zoom over to my screen situation. Here we go. So let's suppose we're rotating about the x-axis. Let's just keep it as the x-axis right now.
Mm-hmm.
So what you've got is you've got your curve. There are two methods, each one distinctly different. And so what you do with one method is not the same as what you do in the other method. So that's important. So do you want me to talk about the disk first and then the shell second?
Yeah.
Okay, so imagine that we have a curve and it goes something like this. I'll call it y equals f of x. And I'm going to do a disk method. And so I've got my shape and it goes something like this, goes something like this. And in this particular situation, what you have to imagine, do my green thing, is your rectangle will look something like this. And if you imagine that point there as being x comma y, right, then you talk about this as being position x, right? And this here is position y, right? So we need to know in this question who the radius is and who the height is. So this is the simplest situation. Because we're on the x-axis, at least, it's the simplest situation. So we need to know radius and we need to know height. So when we do it in this particular combination, the formula doesn't have a height because the formula just has pi radius squared, right? So what is the radius? The radius is the distance from here to here. So the radius is the distance that is.
So that would be the function, right?
So that would be the function. So in that situation, the formula looks like that. Now let's take that same picture and rotate it about a line like y equals 3. Now we still have the same start and finish. We have the same rectangle, but the formula for the volume is now going to be what we call pi big radius squared take away small radius squared. In this case, that distance from there to there is the small radius. And this distance from here to here is going to be the big radius. You can imagine that point there, right? From here to here being the y value. Y equals f of x. So the big radius is that bit plus a y. So the big radius, right over here, is going to be that distance plus this distance. So that's going to be a 3 plus a y, and that's going to become 3 plus f of x. So whatever f of x is, 3 plus f of x is the big radius. Now, what will the small radius be in this situation?
3.
And it's just a number, right? And that takes care of that situation. Now let's do the ultimate version of this, where we have y equals f of x. We have another one up here. call it y equals, I know, g of x. And it's going to start here. It's going to finish here. And we are going to rotate it down here at y equals 3 again. Let's see what happens to our rectangle this time. Well, based on distances, the short distance, 30 there, is small radius, and the big one is that one. So my volume is going to be the integral from A to B of pi, the big radius squared, subtract the small radius squared, dx. This big one and this small one go different heights. One reaches the height g of x, the second one reaches the height of f of x. Right? So when I'm looking at what these are equal to, the big one, which is here to here, is made up of two pieces. It's made up of this distance, which is 3, plus the height. So this is going to be 3 plus g of x. The small one is very similar. It's made up of this bit plus the height. And this is 3 plus f of x. So if you go in here, you're going to do the big one, in this case, that one happens to be. And g of x are just placeholders for whatever function happens to go there. Now, each of these two guys, I have put the axis of rotation parallel to the x, but I've put it below the guy. So what's going to happen if I take that same picture, there's my y equals f of x, there's my y equals g of x, and I start here and I finish here, but I rotate about a line that's way up here. That's the shortest one of the two. That's the small radius. And this one, that's the large radius. So as long as I can find out who these two guys are, I've pretty much done the question. So let's find out how you find the small and the large, or the big. Keep switching between word big and large and so on, but it's the same word, same thing. Right. How are you going to get that distance? Well, if you wanted to only find this distance from here to here, couldn't you find the total distance from here to here, which is 10, and then take away the height of the function? So won't this distance be 10, take away this piece, g of x? Do you see how it's now not add, but take away? And if you want to get the other fella, so once you've figured out what one is, you'll quite soon realize that whatever you do to get the one, you do the same thing to get the other. And so whatever f and g are, these are the guys I will use in big and small and squared and so on and so forth. So what we've kind of covered here are all the permutations of one or two curves, x-axis or parallel to the x-axis situation. So there are lots of combinations out there, I guess. Single function x, double function x. single function parallel to x, double function parallel to x. Have the line below the x-axis, have the line above the x-axis. You see all the different permutations, but they all boil down to finding these two things. What's the biggest distance to the axis of rotation, and what's the shortest distance, and making sure that they're in terms of x. So how do you do y? Can you just imagine the shape's turned on its side? Can you see then that the furthest one is going to be your big, and the shorter one is going to be your small? So the one that's furthest to the right, isn't that going to be your big, and the one that's not is going to be your small. So if you draw a picture of the thing, you can visualize the up and down ones, which we have covered. But if you imagine everything just doing a little 90-degree turn, isn't it all about left and right? And when you measure the distance, you'll be finding f of y and g of y, right? Because it'll be in terms of y when you go horizontal, right?
So is it going to be the same for the shell method too?
No, in the shell method, all bets are off. In fact, it's best not even thinking about the shell, the disk method when you're doing the shell method. Just don't even think about them. They hurt your thought process rather than help it. Now, let's show you what that fella looks like. The only thing that really makes them similar looking is that, what am I rotating this about? Okay. Is that you take some area and you rotate it about an axis. So that's the similar part. But the way you go about it is quite significantly different. So let's suppose I wanted to rotate something about the y-axis. Now, if I'm doing the disk method, if I rotate something about the y-axis, don't you do everything in terms of y, right? It'll be distance, big guy squared, take away little guy squared, dy. But in the shell method, it's the integral from a to b of 2 pi radius height dx. So how do you find those guys? Well, you build a rectangle. Here's the first difference. Do you notice that the rectangle is parallel to the axis of rotation? When we did the disk method, do you notice that the rectangle was at right angles? Right, it was perpendicular to it. So even the way you draw your rectangles are different in the shell method. Y-axis, vertical. Y-axis, axis. That's different. Pretty much everything is different. Right, now, the guy we call height, is that guy there? In this particular question, isn't the height just the value of the function? The distance from there to there is the y value. Now, the radius is the distance from the rectangle to the axis of rotation. Now, if you imagine that point as being x comma y, won't this distance be y and that distance there be x? So the radius is x. And you end up with the integral from 0 to pi, 2 pi x, f of x, dx. So provided you're rotating about the y-axis and it's a single function, that's the formula that will get you the volume. So a single curve being rotated about the y-axis, this is the formula that will get you, right? Now, if you start moving things around, then all bets are off. Let's suppose I take the same function but I decide to rotate it about this line over here, which is what, x equals -3. If I put my little random rectangle, that distance there is x, this height here is y. Good. Let's see what we get now. The radius is that distance there. The height is that guy. So the volume is going to be the integral from A to B of 2 pi radius height dx. Now, that position there is x. What do I mean by x? I mean that distance there, right? Is x.
Would you add 3?
Yes.
Because that's how much farther away it is from the x-axis.
You would do exactly that.
And then the y is just a function?
Yeah.
Okay.
Begin to click.
Yeah, I think so. Could you do like a really quick example of a subtraction one? Because that's the ones I'm having a hard time with. Is it just like...
Yeah, yeah. The subtraction one is really just a matter of where the axis of rotation is. So let's have it way over here at x equals 20, right? Here's my little rectangle. That distance is x, right? This distance is y. The radius is the distance from the rectangle to the axis of rotation. Okay, now, the total distance from the y-axis to this line is 20, right? That total distance from here to here is 20. The distance from here to the rectangle is x. The piece that we want is the other bit, right? Which we're calling the radius. Can you see that 20 take away x is that guy? And so when you do your integral from A to B, 2 pi radius height dx, you're really just going to go and do, oh, I forgot to write that down. The radius would be 20 take away x. And won't the height just be the value of the function? Now, what I haven't done, but actually it's very easy to do here, is do you imagine it wasn't just f of x, but another piece here going g of x? So there's two curves. Do you know the nice thing is that they're dead easy to cope with. See if it's a top curve and a bottom curve like this, f of x, g of x, isn't the height just f of x take away g of x?
Yeah.
And so you just change that to an f of x take away g of x, and that takes care of that. Now, if you do everything the other way around, don't you just do the same job, but now everything's y's instead of x's? So it's x equals y cubes, and x equals f of y. But the process is really just.
But you're still trying to find the radius and the.
Yeah, you're still trying to find the radius and the height.
It's all the same. Okay.
All
great.
the same.
Thank you.
You are welcome. Are we good, Trenton? Have you any questions?
I'm all good, yeah.
Okay, then if that's it, I'll call it a day and I'll see you tomorrow.
Thank you.
You're welcome.
Thanks.
Oh, guys, do you mind if I actually take this bit of the video and stick it somewhere so others can see it?
For sure.
Yeah.
Okay,
Sure.
thank you. I might just tag it on actually at the end of this video. It's probably easiest. Okay. Right. Well, thank you again. Bye-bye.